The optimization in the case of Falcon 1 was really in terms of a cost per flight to orbit. So it wasn't a cost per unit mass optimization. It was what is the smallest useful vehicle that we can build and deliver satellites on, and we concluded that was yet to be at least sort of 1,000 pounds to LEO, and we ended up exceeding that, going to about 1,500 pounds. Total cost per launch is about $6.5 million all in. Both stages, LOX kerosene. One noteworthy element is that the first stage is intended to be reusable. It comes back via parachute to a water landing. The pricing does not include any assumptions for reusability. I'm actually fairly confident that reusability will work, provided the parachute opens. I mean, I think if the parachute opens, I don't think the seawater is going to hurt the rocket. If you see what it goes through on the test stand and on the launch pad, where it gets deluged with water, high pressure water, and in our test stand in Texas, we've had sleet, snow, rain that's hitting you sideways at 35 miles an hour, extremely high winds. So I think if it provided we get it back, I think it'll actually be require very little refurbishment in order to launch again. The first stage engine, which we call Merlin, is of modest performance. I mean, one of the things that we haven't tried to do is try to achieve the highest possible performance. Our goal has been to create something which is a reliable truck, essentially, rather than a Ferrari. So we haven't produced, for instance, a stage combustion, super high ISP engine. This is, you need to be pretty good, but to get to orbit at all. But you don't really have to push the envelope any further than we pushed it here. Our upper stage engine also LOX kerosene, and similar in architecture to the first stage engine, except that it doesn't have a turbo pump, and it's a low pressure. The Falcon 1 development has really been winding down now for the past several months, and essentially is almost complete at this point. So the development focus for about the past year has been more on the Falcon 5, which is our medium lift vehicle. It has engine out capability, so you can lose any one of the main engines and still make it to orbit. I think that's actually a very important principle, given that airline transportation, almost all airliners have multiple engines. So if you lose an engine, you don't go down. Jet turbines are far more reliable than rocket engines. So if that principle makes sense for jet turbines, it really makes sense for rocket engines. And we expect to be able to accommodate up to a 5-meter fairing as well. So it'll have, really put some pretty big stuff up there. What is the throw weight of Falcon 5 to Mars? Well, it depends on which trajectory. I mean, the 0C3 number, as I recall, is about 1,200 kilograms, something like that. Yeah, it's like about a ton, a little over a ton. I mean, basically, it's about as capable as the Delta II Heavy is that sent the Mars exploration rovers there. So anything that Delta II could throw to Mars, Falcon 5 could throw to Mars. Couldn't really send people if they were alive. Needs something much bigger than that. But you could certainly do robotic missions. We don't like to disclose too much ahead of time because, well, frankly, we'd like to. It's more a question of sounding credible than anything else, because we'd like to get some things accomplished before we claim we're going to do other things. But the plan is to do a vehicle which is in the class of Delta IV after Falcon 5. And you could apply sort of a common booster core approach to that, and encompass the entire range of the ELV capabilities, so up to about 60,000 pounds to orbit, maybe a little beyond that. I can say that we'll be announcing something fairly significant later this year, as far as much more lift capability than is currently represented. But we'd like to, ideally, I'd like to have Falcon 1 launch before we make any big announcement in that direction. But you can expect that from a strategy standpoint, we're, call it the 7-Eleven strategy. We're going small, medium, large, and extra large, or big gulp, or whatever it is, super big gulp. So Falcon 1 is obviously small, Falcon 5 is medium, we'll have it large and extra large. Range-related stuff is probably, all regulatory stuff combined, I'd say at most 25% of the cost. It's material and significant, but it's probably 20 to 25% of the total cost associated with both development and launch. The ablative portion is actually really cheap. It costs less than one of our main valves on the engine. I don't want to give away sort of really detailed proprietary numbers, but I can say it's really de minimis. It costs us more to hire the tugboat to go out there than it does to replace the ablative. Then, as far as the actual launch date, we think we'll be ready to go as soon as the Titan IV departs, which is currently scheduled to be around mid-July. There's a contingency there both on the Titan IV rocket as well as the payload, which is a classified payload. They won't give you specifics when there's classified stuff involved. We expect, assuming that they launch in mid-July, we expect the range would give us a launch, because the range has to assign a launch day to us. We assume the range would assign a launch day that is within 2 or 3 weeks of the Titan IV departure. So therefore, if Titan IV left, I'd say basically August would be a good bet. And then as far as Kwajalein, that's actually going very well. We have our own little island there called Amalek. We expect to have that launch site active and ready to do something with in the late August timeframe. So if Titan IV gets significantly delayed, then we'll go out of Kwajalein. And we expect to actually have 2 rockets, one at Vandenberg, one at Kwajalein, possibly on the pad at the same time. Actually, we try not to tell anyone outside the space business that it's for a rocket, because they assume rockets are made of magic. So if you tell them it's for a rocket, they go like, well, I don't think I'm quite good enough to do something for a rocket. And they're like, no, it'll be fine. So we generally, there are some suppliers or aerospace suppliers that do a good job. I'd say like Murata Valves does a good job, for example. Spincraft does a good job of spinning domes. There's a few. I don't want to sort of paint all aerospace suppliers with the same sort of negative brush. I think there are definitely some good ones out there. But generally, we find if you want something cheap, fast, and it's probably going to work, then you should use a regular commercial supplier. If you want something that's expensive, takes a long time, might work, use an aerospace supplier. We don't want to be the ones begging to use facilities. So if we're going to use a NASA facility, then that NASA facility has to behave like we're the customer. If they don't behave like we're the customer, we're not going to work there. If we have to sort of justify why we want to work there, we're definitely not going to work there. I think just for pace of execution reasons, because there's also a lot of paperwork involved with using NASA facilities, we've chosen to use our own facilities. But I think, like I said, for big stuff or where that's it's like one of a kind of test facilities, that's probably where it tends to work with NASA.